Okay, so today we want to look at a Freyer model for a multiplication fact, and it's a simple one. We're going to start out with 3 times 4, and there's a couple ways we can break this down, and I think visually, if we have something that we can use as a reference, that'll help us out. So first off, we're going to start with our first visual representation here, and what I'm going to do is I'm going to just take our 4 times 3, and we're going to do rows, right? So we're going to say a row of 4, 3, 4, and we have 3 of them. So we're going to do a second row of 4, and a third row of 4. So we've drawn all our objects here, but sometimes we don't look at these, we don't summatize it, we don't sit there and say this makes sense to me visually, right? So what we need is sometimes a shorthand or a quicker way or an easier way for our brain to understand it. So one of the ways we can do that is by counting by something that's a little bit more natural than counting by 3s or 4s, and that's counting by 5s. We have 5 fingers on each hand. A lot of times we can kind of rattle off those facts, 5, 10, 15, 20, and we know how to count like that. It builds up a rhythm in our brain that we understand. So to turn these into rows right here, or columns of whatever number we want, we can aim for something where we come up with rows of 5. So to do that, we already have 1, 2, 3, 4. So what we need to do is we need to borrow from somewhere else. So if I'm going to put in a 5th point here in each of these, well, I'm going to have to borrow that from somewhere. So I'll just take it from this bottom row. Right? And then we'll do the same thing for this one and steal from this bottom row. And these are not going anywhere, as far as leaving the problem. They're just moving, right? So now we end up with 1, 2, 3, 4, 5. And we can count these by rows of 5. So 5, 10, and then what's our remainder? Well, we have 2. So 10 plus 2 gives us 12. And that's an easy way to think about that. But what if we want something else? Well, we can also break it down into something that's easier for our brains to understand by going with an even smaller number. Instead of 3 or 4 and going up to 5, we can go down and we can go to 2. So we know 4 is just 2 times, right? So when we were doing our drawing over here, we said 1, 2, 3, 4. Well, what if we break those apart, right? We can just say 1, 2, and have those very close to each other, and then 1, 2. That gives us our 4 right there. So we've taken one of our 4s and we've split it up. And we can continue to do this. We know we're going to have 3 rows of these broken apart 4s in sets of 2. And now we're just working with 2s. This is easy. So 2, 4, 6, 8, 10, 12. And that's going to be our answer right there. So we've come up with a way of breaking this down to a smaller number that makes sense for us. Okay. Now if we look at some sort of a word problem, what I want to do is I want to say, if we have a way of coming up with an easier way of looking at this in a word problem, because sometimes that makes more sense to people. So I'm going to aim for if 3 children all bring 4 toys to the playground. I'm going to have to pin this down with my elbow because this is actually kind of awkward to hold this camera and do this at the same time, but we'll figure it out. To the playground. How many toys total can they play with? And for this one, we could do a little visualizations. We could draw little smiling faces of these children, and there are 1, 2, 3, 4 toys, and we can continue that out there. But we have the basic idea of this being a word problem, less a visual problem, but we can always enter that in. So one of the ways that was just taught to me this year of figuring out things like this is someone called it the Japanese method. I don't know if I've heard it called that before, but what you're doing is you're just taking your individual points, and this works better when you're doing like 2-digit multiplication. But what we can say is we're going to draw 3 lines. Again, I have to pin this down. Should have done this on a clipboard. And then we're going to take our second digit, our 4 here, and we're going to draw 4 lines in the opposite direction. And what we do here is we end up counting the intersections, how many times these make a point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that is going to give us our answer to the word problem through another visual method.